So, hello everyone again. This is lecture 2 part 3 of wave optics. I am Sameer Levankar. Let us begin our discussion. So, just a little bit course outline for you. We started with the introduction chapter of wave optics, a little bit about what is the difference between the corpuscular model of theory, model of light and the wave theory of light. Then we started with the Huygens principle. In this we first studied about the wavefront concept, then how using Huygens principle, if we know the wavefront at t is equal to 0, we can calculate the shape of the wavefront at t is equal to tau. And right now we are in the third part, that is refraction and the reflection of plane waves using Huygens principle. Refraction concept is almost completed, and after the completion of little bit discussion is more required, and after that we will be starting with the reflection of plane waves. So, let us move on with the discussion. So, this was the last point which we studied in the concept of refraction and reflection of plane waves. So, finally what we got was sin I by sin r is equal to V1 by V2, and using the refractive indices of medium 1 and medium 2, the final equation which we got is n1 sin I is equal to n2 sin r, which is also known as the Snell's law of refraction. So, please remember this formula quite clearly, this can be used in your exams also. So, n1 sin I is equal to n2 sin r. For example, if the value of n1 is given to you, angle of incidence I is given to you, and the n2 is given to you, in exams it can be asked to calculate the value of r. So, let us move on with today's discussion now. So, please look over here carefully. Now, further, if lambda 1 and lambda 2 denote the wavelengths of light in medium 1 and medium 2 respectively. So, wavelength of light in medium 1 will be lambda 1, wavelength of light in medium 2 will be lambda 2. So, further, if lambda 1 and lambda 2 denote the wavelengths of light in medium 1 and medium 2 respectively, and if the distance BC is equal to lambda 1, let us suppose we are assuming that this distance BC is equal to lambda 1. This distance is equal to lambda 1, then the distance AE will be equal to lambda 2, then this distance AE will be equal to lambda 2, because if the crest from B, what is the reason between this, how can we say that if the V1 tau is equal to lambda 1, how can we say that V2 tau is equal to lambda 2? The reason is written here only. If the crest from B has reached C in time tau, so if the crest, what is the crest here, let us say I say this as a crest. So, if the crest has reached B, if the crest from B has reached C in time tau, then the crest from A have also reached E in time tau. So, it does not depend on the velocity variation also, it depends on the time. So, crest, movement of crest is a function of time, that is why if the wavelength value is equal to V1 tau in BC, then wavelength 2 will be equal to V2 tau. So, this was the reason behind this. Now, thus lambda 1 by lambda 2 is nothing but BC by AE, and we know the value of BC is V1 tau, we know the value of AE is V2 tau, tau getting cancelled, hence we will get V1 by V2. Therefore, from this what we get is the ratios of the wavelength is nothing but the ratio of the velocities, or the ratio of wavelength to velocity, velocity to wavelength will be equal to the is constant, that is V1 by lambda 1 is equal to V2 by lambda 2. So, this is one of the one relation we got from the simple mathematical formulations after the Snell's law of refraction. Now, the above equation implies that when a wave gets refracted into a denser medium. So, now what will happen is, let us suppose that V1 is greater than V2. We are assuming that a wave gets refracted into a denser medium, that is V1 is greater than V2. The wavelength and the speed of propagation decreases, but the frequency remains the same. So, what does this line says? Please pay quite attention here. What it is saying is, let us say V1 is greater than V2, that means this value is higher, this value is lower. That means to make this complete thing constant, the value of lambda 1 should decrease and the value of lambda 2 should increase. This is the first line being written here, that the wavelength and the speed of propagation decreases. So, wavelength decreases and the velocity decreases and the wavelength increases for the second part, but the frequency remains the same. Frequency as in V by lambda is nothing but the frequency. So, frequency can be denoted by f also, it can be denoted by nu also. So, this is equal to nothing but velocity, let me write the velocity by V only, divided by lambda is constant. So, V by lambda is always constant, that means the frequency is always constant. So, this is the thing we calculated or found out from this last line here. Let us move on to the next slide. So, that was the complete concept of refraction. Now, let us move at the opposite variation, that is, if the refraction is being done from a from a medium which has a velocity higher than the second medium. Earlier the incident was being like this, in which the velocity of medium 1 was greater, this time the velocity of medium 2 is greater. So, it is just opposite form. So, just now please just look over here carefully, it is a similar thing only, just the tilting will be in the different direction now. So, now we consider refraction of a plane wave at a rarer medium, that is V2 is greater than V1, quite evident, similar theory as applicable in the last slides. Proceeding in an exactly similar manner, we can construct a refracted wavefront as shown in the figure. So, how is this wavefront being formed? Let us suppose this is the propagation direction. Now, we will try to find out the value B such that BC is equal to V1 into tau, and then we will try to make this incident wavefront AB, which is at an angle of I also here. So, now we have the incident wavefront. Now, at the refracted wavefront, what will happen is we need to find out the sphere, we need to make a sphere with A as the source, with A as the center, having the velocity as V2. Therefore, the radius of V2 into tau will be formed, let this be the sphere. Now, we will make a tangent plane such that from E such that it passes through point C. So, after this we will get a refracted wavefront as C. So, this was the complete procedure also allotted in the last point also, again we allotted that point only here. But this time, as you can see, the variation is somewhat different. The V2 was smaller in the last point, this time V2 is greater than the V1 point here. So, this is the little change from the last point, this is a little change in comparing to the last point. So, this point is done, this point is being done. Now, the angle of refraction will now be greater than the angle of incidence, quite evident that this time the value of refraction will be greater than I, that is the normal, that is the incident ray goes away from the normal. Just to explain to you, let me make the diagram here only. So, let this be the interface, let this be the normal, let this be the incidence. So, this time what is happening, it is going away from the normal, or just to make so this is same thing only if it is coming from downwards. So, if this is coming from downwards, then it is going away from the normal. So, this is the thing being talked about here, let this be angle I, let this be angle R, let this be angle I, let this be angle R. So, this is the concept being talked about here. Moving on. So, the angle of refraction will now be greater than the angle of incidence. So, this point is also talked about here. However, we will still have n1 sin I is equal to n2 sin R. So, this equation, this Snell's law of refraction is always valid. It does not depend that the angle of incidence is coming from a rarer medium or a denser medium, that is angle of the light is coming from a rarer medium or a denser medium. So, however, we will still have n1 sin I is equal to n2 sin R. Now, we define an angle IC by the following equation. Now, let there be an angle such that sin IC is equal to n2 by n1. Let there be an angle such that sin IC is equal to n2 by n1. Now, please look over here carefully, very important concept, very critical concept. So, now thus if I is equal to IC, let us suppose that I is equal to IC. What is IC here? This is IC here. So, what will happen is, let me change. So, n1 sin IC is equal to n2 sin R. Now, we know from this equation, let me denote this equation as 1, that sin IC is nothing but n2 by n1, which is equal to n2 sin R. What happens is n1 getting cancelled, n2 getting cancelled, therefore, sin R is equal to 1 or R is equal to 90 degree. So, this is something new we get. So, what happens is, thus if I is equal to IC, then sin R is equal to 1 calculated here, mathematical formulation being done here, and R is equal to 90 degree. Obviously, for I greater than IC, there cannot be any refracted wave, quite evident that what is the maximum value this refraction value can get. So, this medium 2, if this is the acute angle, the maximum value that R can attain is this, that is the refracted wave can go like this. the refraction, if the refraction is happening, it is quite evident that the value will be in the medium only. The ray of light will go in the medium 2 only, it can't go in the first medium. If it is going in the first medium, then it is the case of reflection. So, if I is less than IC, that is if I is greater than the critical angle, that means there is no refraction being happening, and hence this concept being talked about here is known as total internal reflection, which you already also studied in the ray optics concept. So, just to iterate to you the complete line here, thus if I is equal to IC, then sin R is equal to 1 and R is equal to 90 degrees. Obviously, for I greater than IC, there cannot be any refracted wave, quite evident. Thus, angle IC is known as the critical angle. So, sometimes the question can be asked, please define critical angle and write its equation. So, what you will write is, you will need to explain this complete line here, and then you will write that sin IC is equal to N2 by N1. So, the angle IC is known as a critical angle, and for all angles of incidence greater than the critical angle, we will not have any refracted wave. Quite evident, it cannot be refracted because the refraction cannot happen in the medium of incidence only. If the refraction is happening in the same medium, then it is not known as refraction, it is known as reflection, and the wave will undergo what is known as total internal reflection. So, this is how the total internal reflection is also being understood using the wave propagation theory of light. So, this is completed. This is the final conclusion of this point also. Let us move on to the next slide. So, now the refraction concept is completed. Just to conclude to you, just to make a brief about the refraction concept, we started with the refraction at a denser medium. So, in that chapter what we studied about is, first of all we made an incident wavefront, and we made a refracted wavefront. Then finally what we got, the formula is Snell's law of refraction, that is N1 sin I is equal to N2 sin R. Then we did the same thing for refraction at a denser medium. So, that time also only the refracted wavefront's direction was changed because the velocity v2 tau is changed, hence the radius is being changed. The radius was this time greater, but doing the refraction either in denser medium or in rarer medium, always the Snell's law of refraction is evident, that is sin I, N1 sin I is equal to N2 sin R, where N1 and N2 are the refractive indices of medium 1 and medium 2 respectively. And finally, what we got to know is, if the, let us suppose there may be an angle IC such that sin IC is equal to N2 by N1, then using the mathematical formulation what we got is, IC is the critical angle at which if I is greater than IC, then there can be no refraction and only total internal reflection occurs. So, this is how the total internal reflection was being understood using the wave theory of light, wave propagation of light or wave theory of light. Now, after the refraction is completed, let us move on to the reflection of plane wave by a planar surface. So, now let us understand how the reflection is being understood using the Huygens principle. So, now reflection of a plane wave by a planar surface. So, just first of all look at this right figure, just to iterate to you what is happening here. Let Mn be the surface which has the reflective properties, let AB be the incident wavefront, and let EC be the refracted wavefront. So, how it is happening, I will make you understand, and it is the incident wavefront is happening at angle of incidence I, and the refracted wavefront is entering or moving away at an angle of incidence R. So, now let me explain to you the complete concept. So, now consider a plane wave AB incident at an angle I on a reflecting surface Mn. So, Mn was being talked about to you, and this AB plane wave is having incidence at an angle I. So, I is also given to you here. Now, if V represent the speed of the wave in the medium, and if tau represents the time taken by the wavefront to advance from point B to C. So, what is B here? B is this point. What is C here? This is this point. So, this is nothing but the simple construction or the same construction which we used for refraction concept. So, here let BC is equal to V1 multiplied by tau. So, that is only given to you, hence because there is no need of any two mediums, then we can directly write V1 as V only, there is no use of subscripts. Hence, BC is equal to V into tau. Now, in order to construct the reflected, please make sure it is reflected and not refracted wavefront. So, in order to construct the reflected wavefront, we draw a sphere of radius V into tau from point A as shown in the figure. So, now a sphere is being drawn, this is the sphere being drawn. we draw a sphere having the radius. So, radius given to you as v into tau, because the medium is same, hence the velocity will be same. If the velocity is same, the radius will be v into tau only. There won't be any v2 or v1 applied in this concept. So, in order to construct the reflected wavefront, we draw a sphere of radius v into tau from point A as shown in the figure. Let CE represent the tangent plane drawn from point C to this sphere. So, now we will make the tangent. So, there can be many tangents, but from point E, from this point, that means we need a tangent from point C such that it is a tangent to this sphere. So, we get CE as the that tangent plane, and this, hence this CE is nothing but the refracted wavefront. So, obviously AE is equal to BC is equal to V into tau, quite evident, BC is already known to you. AE also we calculated AE using the radius as V into tau. So, therefore, BC is equal to AE. If we now consider the triangles EAC, please make sure which are the triangles being talked about here. Just to explain to you in much detail, I will make this using two different colors. So, EAC. So, EAC is this triangle here. Let me draw it here for more clarity. So, this is EAC, this is ABC or BAC. So, these are the two triangles given to you. We will find that they are congruent. So, these are congruent because everything is same. Let us say AE is equal to BC, EC is equal to AB, and AC is always common. Also, as these are congruent, hence they are similar. Therefore, the angle of incidence I, where is the angle of incidence here? Let this be the angle, and this be the angle being talked about here. So, this is the angle I, this is the angle R. Therefore, angle I is equal to angle R. So, this is how the angle of incidence is equal to angle R property is being talked about in refraction, and using wave theory of light we can even prove that angle of incidence is equal to angle of R if the reflection is being happening from a reflecting surface. So, this is nothing but the law of reflection. So, now after the complete concept of refraction and reflection is being talked about, we need to consider some of the different forms of discussions being talked about. If a prism is being happening, or if a convex lens or a concave lens is being happening, how the wavefront will be formed and how the different concepts can be applied analogous to the ray optics. So, once we have the laws of reflection and refraction, the behavior of prisms, lenses and mirrors can be understood. Here we describe the behavior of the wavefronts as they undergo reflection or refraction. So, for this lecture only I will conclude by this point only. In the next slide I will explain what is happening in this B part. So, in the figure A we consider a plane wave. So, this is a plane wave as it is passing through in perpendicular direction only. So, in the figure A we consider a plane wave passing through a thin prism. This is nothing but a thin prism given to you on the figure. Clearly, since the speed of light waves is less in glass, the lower portion of the incoming wavefront will get delayed. So, quite evident that the velocity will get delayed because this is the major portion which is thick, and because this is small the velocity will not get delayed, and hence this portion will go slightly higher because it has a greater velocity for some duration of time, and this will get lower. Hence, the wavefront will attach to this plane wave and then keep on tilting, and when it will come forward it will be in this wave and then it will go down. So, this is the concept being talked about here, just to iterate to you again, and that will be the end of this lecture. So, in the figure A we consider a plane wave passing through a thin prism. Clearly, since the speed of light waves is less in glass, the lower portion of the incoming wavefront which travels the greatest thickness, quite evident this lower portion will go through major thickness of the glass, will get delayed, resulting in a tilt. So, there is a tilt here, quite evident the tilt is here in the emerging wavefront as shown in the figure. So, this was the concept of application of behavior of prisms if the light is being analyzed as a wave. In the next slide we will get to know how a convex lens, concave mirror, etc. Have converging property or diverging property as far as wave propagation of light is concerned. So, for this lecture I will stop it here only. So, the course progress for you, we started with the concept of introduction, completion of Huygens principle, and today we are in the third chart, that is refraction and reflection of plane waves using Huygens principle. After this discussion is completed, a new concept called as coherent and incoherent addition of waves will be explained to you in much detail. This is very important concept. And then interference of light waves, Young's experiment, a beautiful experiment by Young's need to be explained. And then finally, the applications such as diffraction and polarization will be done, and that will be the end of wave optics. So, for now, thank you.